how can I start? So I'll be talking about what AI is and machine learning in the context of medicine and what we call precision health. And next time we'll talk about the singularity and how AI will be part of this evolution towards the singularity. And then the third session we'll talk about more technical things about how machine learning is. This is the plan. It may change as I'm going through. So today, AI and medicine. What is AI first? So I decided to tell you about a case that we can understand. You know that currently there is an Ebola epidemic in the Democratic Republic of Congo. There are 3 people who died already. It's not a huge outbreak like in the past, but it's serious enough that the media is now talking about it, for those who are interested in Africa and in medicine. But in 2014, there was a huge outbreak. It was involving many countries, and it became a threat to the rest of the world. And that's why it was very, very serious. So Ebola, what happened is that in the beginning, so this started in the end of 2013, there were many people going to the hospital and they had very common symptoms, fever, diarrhea, and stuff like that. And in the beginning, they didn't know what it was. They thought it was actually cholera. Because they found bacteria, they said, well, this is cholera. They were treating it as cholera, and very quickly, doctors, nurses in the hospitals were dying as well. And it encompassed many, many countries in Western Africa. It's only later, towards March 2014, so that's 4 months later, if not 5 months later, that the World Health Organization realized that it was Ebola and said that let's treat it as Ebola now. By then, many countries in Africa were touched, and that meant also threat to the rest of the world because of modern transportation. You have connections everywhere. So the first thing they have to do when they have an outbreak like this is to identify where did it start. Okay, where is patient 0? By then, of course, patient 0 died and it's gone, but they have to go back in the hierarchy and see who got it from who got it from who, and so they used actually machine learning related techniques called social network analysis to come up with the big graph. This is only part of it that was published later on by the World Health Organization when they reached the top. And they identified the little boy who got the virus first. Why are they interested in the patient 0? Because they want to know where Ebola came from. Okay. And most of the outbreaks, at least they know, some of the bat species that are the Ebola reservoir means that they have the virus and they don't get sick from it. And when humans are in contact with that bats, then they may contract the virus. So they realized that indeed that patient 0 was, I think it was Emil, was close to some bats. The bats by then had disappeared because there was a fire and they burned the tree. It was a long story. But the bats that are typical Ebola reservoirs are these bats that are fruit-eating bats. But the bats that were living next to the house where Emil was playing were not fruit-eating bats, but insect-eating bats, which is new. Oh my gosh, we didn't know that these bats were also an agent to propagate this kind of virus. So what they did, they decided to study the different kinds of bats, the different species of bats, and try to identify which ones actually could be this Ebola reservoir. So they used machine learning. And with machine learning, what they did, they introduced all these features of the different types of bats that they have. So these are biological characteristics. They have 57 variables of different bat species. Some that they know are Ebola reservoirs, some that they don't know. And they built a predictive model. So they try to predict which species could be Ebola reservoir. And they build what we call a decision tree. If we have time, the last session I'll talk about decision trees. So they build the decision trees, they use that decision tree to predict, and they know which ones are actually Ebola reservoir or not, and they measure the accuracy of that predictor, and they improve the model until they got a model that is more or less acceptable for the accuracy, and that told them which type of bat could be an Ebola reservoir. And that was quite interesting because when they put them on the map, they thought that this is where the Ebola reservoir is, but when they put the new ones that they discovered could be also Ebola reservoir, they found that actually they spread in other parts of the world. And there could be a very high risk of Ebola outbreaks in Asia. So, for example, Thailand and Vietnam and Malaysia and so forth. Yet most of the outbreaks coming from Africa. So, machine learning not only allowed them to identify some types of bats that could be agents to propagate Ebola, but also provided new hypotheses. Why is it that we have outbreaks here and not there? Well, actually, that's a hot spot. That's an interesting thing about machine learning. Well, machine learning wasn't, and AI wasn't used just there for this case. Ebola is not well treated yet. We don't have a cure for it. Okay. So there are some ingredients that they know are useful and have anti-Ebola virus activity in vitro. So they wanted big pharmaceuticals, they want to build a drug that can combat this virus, but they have millions of these commercially available molecules that they could use. They're not going to try all of them, it's too much. Okay. So they again used machine learning to identify which ones of these could be a chemical that has potential, a power to inhibit the virus. And indeed, they identify some of them, like these ones that they tried in vitro, and they saw that indeed they have a very good very good anti-virus activity. So machine learning was also used to identify the drug that we could try to fight Ebola virus. So what is this machine learning? What is AI? Okay. And why are we talking about it today? Because it's not new. It has been around for a long time, but now everybody's talking about AI. Why? Why is it? Then I'll talk about how this can be used in health. We call it precision medicine or precision health. And I'll give examples. Okay. By the way, if you have questions, don't hesitate to interrupt me and ask. Okay. I'll be glad to answer those questions. So, if I said why now, it's because AI has been around for a very long time. It started in the 50s, after the Second World War. Computers were built to decipher the code of the enemy, calculate trajectories of missiles and things like that. They were very specific machines. After the Second World War, so in the late 40s, they started building machines that are generic. They can be programmed to do different things. And the scientists were saying, okay, now that we are at peace, how can we use these machines for the good of the people? And some of these scientists were thinking, oh, actually, these machines we can program to do anything. And human intelligence can be broken down into different parts, different pieces, smaller problems, and if we solve each one of them, put them all together, hey, we can build a machine that is as intelligent as humans. And the way they described it in the early 50s and mid-50s, it seemed actually trivial and it's possible. And they convinced many people, and there was a huge hype, like there's a hype today about AI. It's not a complete hype, but there's a huge expectation about what AI can do. That was in the early 50s, from the 50s to the 70s, but very quickly people got bored. They said, well, there's a lot of optimism here. Actually, we can't do it. This is not possible. And there's a start of a disillusionment. People say, nah, AI is not what it's promising. And they kind of forgot about it. And the funding for research dried out until the mid-50s, the mid-80s. By the way, in this part of the history of AI, they were trying to mimic what humans were doing. By mimicking the humans, okay, we're doing something that looks intelligent, but it wasn't really intelligent. It's only in the mid-80s that a new subfield within AI came back to the surface. This is called machine learning. Machine learning is about teaching a machine how to do things while it learns by itself without programming it specifically for a particular task. Okay? You just program it to learn, and then it learns to do a particular task. And that was used for many applications, and it was very successful. Oops, that's back. So rather than trying to mimic the human, we're trying to teach a computer without programming it. We teach it to do a particular task. And that brought back a lot of hope. Say, aha, maybe we can do now what was promised. Didn't do it very well, except in some applications, until 2010, 2012. Something within, so this is AI, then you have machine learning, and within machine learning there's a subfield now called deep learning. And deep learning surprised everybody, because it's also very old technology that existed, that was created in the 50s. But we didn't have the means to really push it to its limits until these days, and I'll talk about that. And then it proved amazingly efficient at many, and effective at many tasks. For example, recognizing people in a picture, or recognizing the dog from a cat or something automatically, recognizing an image that has a tumor from an image that doesn't have a tumor, and so forth. Recognizing melanoma. It is now doing it actually better than humans. And in many tasks, deep learning outperforms humans. Okay. And this is based on a technology, as I said, that was proposed in the 50s called deep learning. Sorry, it wasn't called deep learning, it was called artificial intelligence. So it's called artificial neural networks. And artificial neural networks in the 50s were saying, oh, we are copying how the neurons in the brain function, but today we know that's not exactly the case. The brain is way more complex than that. But it's a simulation, a very simplistic simulation of how neurons communicate, except that it was very shallow here. Now we have it in many, many layers. It's deep, and that's why we call it deep learning. But the technology existed before, neural networks. So in summary, you have the field of computer science. Within the field of computer science, you have a subfield called artificial intelligence. And it's a subfield like any other subfield in computer science. You have networking, high-performance computing, software engineering, databases, human-computer interaction, and so forth. There are many subfields. One of them is called AI. Now, the size doesn't mean that it's the most important one. It's as important as any other field. But I'm making it big because I'm zooming in. And so within AI, you have a subfield that is called machine learning. And that is part of AI like any other subfield as well. We have like planning, reasoning, computer vision, natural language processing, and so forth. Okay. Again, I'm making that one bigger because I'm zooming in. Inside you have supervised learning, unsupervised learning, reinforcement learning, and within supervised learning, and I'll explain what is supervised learning soon, you have deep learning and other paradigms as well. Okay? So often you will hear in the media, they say, oh, deep learning will do this, or AI will do this, oh, machine learning will do this, and they use them as synonyms. They're not. Okay? There is AI, which inside has machine learning, which inside has deep learning. They're not synonyms. That's a typical mistake that many journalists and reporters do. Okay, so let's dig deeper. What is this machine learning? So machine learning is the process that provides means, so algorithmic means, to a machine to learn from data. So basically, you extract, the machine will extract patterns and trends from the data in order to build models that it will use to adapt to the data as it comes to it. Okay. So here's an artificial brain, and people are starting to talk about this artificial brain and AI, and you hear in the media things like, oh yeah, AI market will be worth $60 billion by 2025. So obviously when you read a title like that, you think, wow, AI is very important to me in my life. I have to know what it is. Unfortunately, people don't dig in enough deep to really understand what AI is, and they use the term without knowing what it is. So you hear other things like, the one who dominates AI will rule the world. Have you heard that? Do you know who said that? Putin, Vladimir Putin. So if politicians start saying that, it must be something important that I don't know. What is it? I don't know what it is. Unfortunately, it's not just Putin saying that. All the magazines, all the newspapers now are talking about AI and talking about machine learning and not giving you enough information so that you create your own definition in your head. And the definitions that most people have come from movies, science fiction, while not really portraying the reality of what AI is. Okay. So what they portray, unfortunately, is this image of them, the machine, becoming as intelligent as us, and then killing us and eliminating us. So it's them against us, which is unfortunately the wrong image that we shouldn't have that kind of image. It's definitely wrong. It's not man versus machine, them against us. Then if you say that, if you start imagining this, you immediately think about survival. This is an existential threat. Okay. And, but the real AI that exists today, you have it in your pocket. That's the level of AI we have. And it's amazing what kind of AI is in your phone. Okay. It does amazing things already. But I'll give you more examples as we go through. So what is actually artificial intelligence? It's not what you saw from these movies. Marvin Minsky, one of the pioneers in the field, who was among the organizers of the first conference on artificial intelligence in 1956, he defined it as the science of making machines do things that would require intelligence if done by human beings. So it's not really intelligent, but it looks, well, at least the machine, if it does things that humans are doing, and they need intelligence to do that, if the machine can do that, well, the machine is intelligent. So artificial intelligence is a discipline trying to get these machines behave intelligently, okay, in order to perform tasks that normally would require some kind of human intelligence. That definition is still vague because we still don't know what human intelligence is. What is a human level intelligence? Each one has its own definition. For me, AI is nothing else but a tool. Okay? So artificial intelligence is an enhancement to our own creativity. We build it to do tasks that we wouldn't have been able to do without it. It's like we build a hammer
because I wasn't able to push the nails with my finger. I needed the hammer. It doesn't mean the hammer now is better than me. I build it, I use it for the purpose that I build it for. Okay, and you'll see many examples. So I don't see it as them against us, but us. There's another term that is used quite often, and it was very common before the big wave of deep learning. Many people were talking about data mining, business intelligence. You heard these terms before? Okay. Very quickly there was a stigma attached to data mining, so people don't want to talk about data mining anymore. They created other terms to say the same. People were worried about their privacy, what is data mining doing, how is the government using it to spy on me, or the company is using it to spy on me, and things like that. But it is around us, and you'll see more examples as we go through. So what is data mining? Data mining is a process in order to discover some useful patterns from large data. So you can see that machine learning is part of data mining, because I'm trying to find also patterns in data to build my model in order to do prediction or solve some problem. Okay. It's the analysis and intelligent interpretation of large data in order to provide some actionable knowledge to decision makers. So the decision makers could be human decision makers, via some decision support, or it can be another process that uses these patterns in order to make its own decisions, like the dog moving or reacting to people around or whatever. So data mining is actually at the confluence of many fields, among them machine learning or artificial intelligence, but you have information retrieval, visualization, statistics, database systems, and others. So the question, why AI is coming back? Why are people talking about AI today, while it was created years ago, in the 50s? Well, because AI went through winters of AI, people forgot about them. There were 2 major winters, and now it's coming back because we have 3 important ingredients that we didn't have before. Number 1, we have a lot of data that we didn't have before. We are collecting more data than every year. Every 2 years, we collect data equivalent to human history before. So every 2 years, so the year before was actually part of those 2 years that is equivalent to the rest of the world. Well, those new 2 years is equivalent to the rest, so it's exponential, what we collect as data. The other ingredients are the fact that our computers are way more powerful than before. High-performance computing evolved significantly. What your cell phone can do, and I will show you examples later. I mean, they are equivalent to the most powerful computer just a few years ago. It's going so fast. And the third ingredient is the fact that now we have also some algorithms that can crunch this data using these computers. And we couldn't, or either we didn't have these algorithms before, or we couldn't run them because our algorithms were not able to run on the computers that were available.
There's a good question. In
Yep.
theory, those algorithms could have been written in the 50s, correct? We just
Some
didn't have
of
the
them
power.
are written in the 50s, or the new ones are based on those
Right.
written in the 50s. But because the computers that we had in the 50s, and even in the 80s, and even in the 90s, were not powerful enough, we had a limitation on the algorithms themselves. Today, we can run them. And I'll explain later on. So what kind of data are we collecting? Well, you can imagine that this is some data from, some statistics from a while ago. I don't remember which, well, this is in 2012 or 2014, I don't remember exactly. They were calculating in every single minute on the internet what kind of data is collected. So you have millions of searches every minute. Now we're counting actually millions of emails every second, not even every minute. How many tweets are sent every minute? How many Facebook shares every minute? How many movies are downloaded on Netflix or on YouTube, and so forth. It's phenomenal. All that information is stored, it's not dumped. So we're collecting a lot of data. So much so that people were interested in measuring it just in the term of, well, in the healthcare, for example, healthcare system. Okay, so this is another slide, I forgot these slides. Where the data is coming from, not just from the internet, from the Internet of Things, from electronic health records, insurance providers, clinical trials, genome data. This is just in the health. So all this information creates a mind-boggling amount of data, and we talk about zettabytes. Zettabytes is 10 to the, I forgot the exponent anymore. So people are interested in actually measuring it to some extent. And there was a paper a long time ago trying to visualize that amount of data, because when you talk about gigabytes and terabytes and zettabytes, people can't imagine what it is. So they said, if I have this amount of information, this is just in the medical domain, and I'll store it in CDs. This study was done in 2007. I store it in CDs, knowing that the CD has 1.2 millimeter thickness. How many CDs do I need to store all this information? If I pile them up, how high will I get? Well, you'll get to the moon. Just piling the CDs with that information. That's amazing. So, a few years ago, people said, well, CDs are nothing. We don't use CDs anymore. We use DVDs. Actually, we don't even use DVDs anymore. But they just looked at the healthcare system in the US. How much data are we creating? And if we put them not on CDs, on DVDs, and they use the same space, then we go to the moon twice. It gives you an idea how much data we are collecting. And we are collecting all this data for well, there are many reasons, but one of the reasons is that the space is becoming cheap, extremely cheap. It's very cheap to create disks and put the data in there. Now, just to give you an idea how cheap this thing is becoming, if you look at the micro SD card, in 2005, the biggest capacity was 128 megs. Okay, a camera like this one. In 2014, so 9 years later, we're not talking about megs anymore, it's 128 gigs on the same space. 2 years later, it became 256 gigs. Last year, 512 gigs in the same space. So you can put 4,000 times more information on the same space. If you look at the price, from the archives you can see these are PR kind of things that IBM was doing, and Pan Am as well was trying to advertise at the same time. IBM was shipping a disk. You know how big that disk is? 5 megs. 5 megs is barely the size of a big high-resolution picture. Okay. That 5 megabyte disk was $120,000. They were shipping it from one place to another, so it wasn't such a big deal that they were taking pictures and putting in the newspaper and things like that. The captain, the pilot, was there just to say, well, I was next to a 5 meg disk. Well, today you can go, well, this was my data that I got from last year, on a famous website. You can buy stuff online, and a 64 gigabyte SD card was $18. Probably this year is even cheaper. So now I'm trying to compare the improvement here. Okay. If I had this disk at that time in 1956, it would have cost $1 billion. I mean, it's unthinkable. It's unthinkable. Today you can have it in your pocket. You may lose it and say, oh shoot, I have to go and buy another one. Okay. So an improvement of 76 million times. It's very cheap. If I look at now high performance computing, how did it evolve? Well, today you can go and buy graphics cards. My son just bought a graphics card this weekend because he wanted to improve his stuff. But anyways, you can buy this to a store here less than $1,000. This is used typically for playing games, okay? But it's so powerful that researchers like myself, we use it for calculations, not for games. And that GPU that people can buy for less than $1,000 is equivalent to a Cray 1 machine that was the most powerful computer a few years ago. Now you can have it on your desktop at home. Why? To play games. So people have kept statistics about the performance development. And here you can see the years from '94 till last year. This is the curve for the best computer every single year. And here you have the performance in terms of how many flops. Flops are the floating point operations, how many basic operations you can do on real numbers. And this is logarithmic on a scale. 1 gigaflop, 10, 110, 1 teraflops, and so forth, petaflops, and so forth. And the green line, this is the sum of all the 500 most powerful computers that year, and this is the 500 most. Anyways, the most important one is this curve here in yellow. You can see that it's going fast because this is a logarithmic scale. It's going up very fast. The most powerful computer in the last few years, it was typically in China. Until very recently, last year, in June last year, the Americans finally beat the Chinese and they developed this computer by IBM, 122 petaflops. By the way, this computer is just made of GPUs, Brazilian GPUs. Well, what is this thing here? That's 1 teraflop. 1 teraflop, the most powerful computer that reached 1 teraflop, that was in '97. That's equivalent to, that's equivalent to the most powerful cell phone you can buy today for about $1,000. Okay, either the Samsung S9 or the iPhone X. So that phone is equivalent to this computer that reached 1 teraflop in '97. That computer was $55 million. It was the size of 1 or 2 tennis courts. Now you have it in your pocket, and you take it for granted. Okay, so that's the computer. It takes a big room, and this is your cell phone on that table. This is how it is today. It's getting very fast. This is the fastest computer today, and this is the fastest computer in '94, '93. That was November '93. What is the improvement here? Okay, this improvement is, did I calculate it? 206,000 times. It's very difficult to imagine what that is. So to compare, I said, well, what if this step that I do today, which is about a yard or a meter, in that same number of years, now my walk improves as fast as the computers, that my one step will become 1 meter, will become 206,000 meters. What is that in kilometers? Well, it's like my step becomes reaching almost Calgary. That's what it means. The computers, their improvement is equivalent to me now having 1 step and I reach Calgary. That's what it is. Or any anywhere else in that circle. Same thing with the space or the cost. I mean, the space is 4,000 times. It's like my step is now 4 kilometers. Or in the case of one step, 1 meter becomes 76 million meters. That's like going around the world twice. Now you can imagine what kind of progress we're making. It's huge. Okay. So it's thanks to these 3 improvements in performance of the computers, the availability of the data, and the sophisticated algorithms that we have AI. Now it's possible. So what kind of improvement? For example, deep learning. So deep learning, as I said, is based on artificial neural networks. Artificial neural networks are nothing else but a simulation of how neurons in the brain, we think they function. Each neuron here receives signals from the dendrites, from other cells, and then at one point decides, okay, I'll send a message on my axon to the other cells. So here you have layers of these cells, each one getting a signal, and at one point deciding to send the signal to the next layer. It's a very simplistic kind of representation of the brain. So each cell here, you have a function that decides to fire a message after receiving messages from here with different weights. So there's an activation function that activates the signal, and that signal can go to many other cells. And basically you have layers, and one layer is an input, you provide information, it's propagated thanks to this activation function until you reach the output layer, and that's the result. But to simulate this, you need a lot of power. And that's why in the olden days, we just had a timid input layer, only one hidden layer, we call this hidden layer, and one output layer. Today, because of the sophisticated computers, we can afford to have many hidden layers. We can simulate a more complex architecture. Okay? And that's why we call it deep learning, because it's deep. But the idea is the same as before, except now that we can have many layers, we can specialize some layers for different things, and we can create architectures that are more sophisticated. So we can even have one that feeds on another, and so forth. So we have what we call convolution networks, or recurrent networks, or LSTMs, and so forth. The interesting thing is that, yes, this is old technology, but people forgot about it. And there were very few people who were determined to continue to work on this because they believed in it. They were very stubborn. And these stubborn people, thanks to them, we have deep learning today, are from Canada. Okay. So Yoshua Benjo is from Montreal and Jeff Hinton from Toronto. There were other people around the world also working on it, mainly connected to these 2 fellows. Why is it coming back? There was an event that happened in between 2010 and 2012, particularly in 2012. There are often competitions, and researchers around the world participate. There was a competition to identify or classify images. So images of animals, recognize which one is the dog, which one is the cat, which one is the rabbit, whatever. And people have been trying to compete and try to get the best results ever. So the competition existed since 2009, 2010, 2011, and you can see the improvement. Okay. This is the accuracy, 70% accuracy, 71% accuracy, 74% accuracy. So they were planning a year, complete year to get to that. Nobody was using deep learning. They were using other techniques in machine learning. And then what happened is that in 2012, a team from Toronto, led by Jeff Hinton, they used GPUs and deep learning architecture. Nobody knew about that, but they won by a long shot. It went from here to 83%, so 10% improvement. So people say, well, what's happening? Well, what are you using? What do you have underneath the hood? I said, well, we use neural networks. We call it deep learning. Aha! Then people started being interested in that, and actually the students who worked on that project were immediately hired by Google. They tried it on their big data set, and it changed everything. And then it started going up, 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 up. This is the typical performance of a human on that task to recognize these images. This is an expert, the performance of an expert. And deep learning did better than the typical human and now better than the expert at recognizing images. Well, it's not just on recognizing images. They tried it. This is the test on the famous test with the cats with Google. But then they tried also with speech recognition. There's another task that is very, very, very tough. It's recognizing what is said in a recording. Okay, so speech recognition. Now you take it for granted, you use Siri, you use Google now, but it's not a trivial task. It's thanks to deep learning that you have Siri today. So there was a task for many, many years, from the 90s. It was run by DARPA. DARPA funds research typically related to the military, but other research as well. In this particular case, they had a data set called Switchboard. It's conversations on the phone, and they want to transcribe them. Okay. If you have a human being, you have to listen to that and write it down. Oh, rewind, listen again. Oh, did you say that? Did you say, oh, it takes forever. Okay. And if you have hours and hours of recordings, you have to have hours and hours of listening and many, many people. So they wanted to automate it. And many companies were very interested in that. They were trying. So you can see here, this is the error rate, so it's the reverse. The lower, the better. So the errors were going down, down, down. Different techniques people were trying. This is different years. And then suddenly they started using deep learning and started going down. And now they're doing better than humans. Better than humans at recognizing what is being said in a recording, so speech recognition. The other tasks, this is for object detection, detecting an object in an image. And again, here they're doing better than the expert. This is a human, this is the computer. There are other tasks like this is translation. This is not against humans, we are still far from humans, but thanks to deep learning it's starting going up. So translation is also from one language to the other is getting better and better thanks to deep learning. There are other tasks like question answering. I provide a text and then questions, and you need to answer those questions based on some text. We're not as bad, well, we are still better than the machines, but the machines are getting, the algorithms are getting as close as possible to the correctness of the humans. So what is this machine learning? How does it work? How does it do it that they manage to recognize these images better than human experts and so forth? So as I said, machine learning is basically algorithmic means that allow machines to extract patterns from data and learn from that data. And those patterns are used to build models, predictive models, to predict the future based on the data that has been seen. Okay, so basically we learn from experience, the data that we see is the experience, and then we predict based on what we saw, so that we can adapt to the new data that is coming to us. And you'll understand better with examples. Okay. So it's a field in AI, and deep learning is one of the different techniques. It's not the only one. And I'll go more in depth about machine learning in another session, but what I want you to remember is that you have basically data that is labeled. Okay, I'm putting here colors as the label. The algorithm goes over it and learns to discriminate between the different labels. And that is built in a model. That model can be many different things. It can be a mathematical formula, it can be a different data structure, it can be hyperplane crossing the search space, it can be also a neural network. So I'll use this nice model to automatically label objects that haven't been labeled before. Okay, so I learn from here to label these automatically. That's what machine learning is. This is supervised learning. Okay. And the question is, how do I use this? Okay, so it can be, as I said, a neural network. There is also another technique that we are known for here at U of A called reinforcement learning. It's also machine learning, and I think I have slides that talk about it. What is very specific about deep learning, however, it has a huge advantage. It has many disadvantages. Okay? One of them is the fact that it needs a lot of data. Another disadvantage is that it's a black box. It doesn't tell you how it made decisions. But one big advantage is the fact that the more data you give it, this is the amount of data you give it, and this is the performance it gets, so the accuracy, for example. Not the original, but the old and other methods for machine learning, they reach a plateau, and if you give them more data, the performance doesn't improve much. They stagnate. They don't know how to take advantage of the extra data. But deep learning, the more data you give it, the better it gets. And that's why it reaches the level of human expertise. It needs a lot of data. We humans, at least, we can learn quickly. I mean, you're not going to give millions and millions and millions of pictures of dogs to a child for the child to recognize what is a dog and what is a cat. Okay. But we reach a good performance. So how can we use this, and what kind of applications this is used in? Well, there are many applications that you're using today, and unbeknownst to you, they have machine learning in them. For example, spam detection. When you use email, some email is automatically put in the folder for spam, and you don't even see it. Okay. Some email is marked as important. How does it know? Well, the machine or the algorithm within the client for email observes you, what you answer and what you delete without reading. Okay. And with enough examples, it builds a model, a predictive model that for you, and not for somebody else that has a different behavior, for you, this kind of email is actually trash. Okay? So it doesn't bother you with that email because it's spam. It learns from your behavior. Another example is in the bank. You go to the bank to ask for a loan. Well, they'll ask you for information about you. Where do you live? Do you have a car? What kind of diploma do you have? Or what's your job? What's your salary? All that information is used because you are compared, between quotes, with other people in the past. So the people in the past that came and asked for a loan, some of them defaulted, some of them paid back. So we learn from all the past information, and we build a model, and that model is used to decide, okay, I'll give you the loan or not. Same technique is used also to detect whether this is a fraudulent transaction or not. When you buy something with a credit card, there is an authorization that is sent to, or a request for an authorization sent to the bank. Well, the bank or the computer anyways that is dealing with these transactions, and very quickly it is run through a model that learned from your behavior, purchasing behavior of the cluster you belong to, and decide, yeah, this is acceptable behavior, it matches the model that we have about this person or not. Okay. We can also use it in medicine, and I have many examples. Wow, time flies. To do diagnosis, prognosis, treatment recommendation, and this is what we call precision medicine. I'll give you one example that some people may think is far-fetched, but it's actually used today, and you can imagine how far we can go. This is the case of, well, this person sitting on the wheelchair is not a paraplegic. He's a student at MIT testing the system. But this is a system for paraplegic people. They can't move their arms, they can't move their legs, but they want the room. Until when do we have it?
I don't think there's something else in there.
Somebody is at the door there.
You can come in, what's it? Okay. Yeah, no, they're just
Okay.
talking.
So this paraplegic cannot use the arms or the legs, yet they would be able to operate the wheelchair. How? Well, we asked them to move their thumb, for example. You got a big thumb. They can't move their legs. But just thinking about it, they will have some activity in their brain is they're sending the order to move the thumb. And we register that. We ask them to do that many times. Okay? And then we ask them, okay, move your, either the thumb or the toe or whatever, move something else. They can't move it, but just thinking about it. And we learn from those signals. And we attach them to the order of turning left, or the order of turning right, or the order of moving forward, or stopping. And now, just by wearing a helmet with electrodes, we can get the signals of their activity in the brain. And by thinking, oh, I want to turn left, well, actually they don't think turn left, they think I'm moving this thumb. And the wheelchair will turn left or right. We can also do the same thing to operate a cursor on the screen. Now, just by thinking, okay, I'm moving my thumb, I move the cursor and I can select A, B, C, D, and I can write, I can type. So these are many uses of machine learning. So how much time do I have?
There isn't any class after here. How many of you have to leave at 3:20? Yeah, so
Okay.
most of
Try
the
to finish.
most of the students can stay. Yeah, we just got
Jump reinforcement learning, I'll talk about it another time. I want to go and talk very quickly about precision health. Give you examples. So precision health, basically the idea is that rather than having, treating all the patients that have the same symptom with the same treatment, not because they have the same symptom that I should treat them with the same treatment. People react to the treatment differently. So how can I personalize the treatment based on not just the symptoms, but the individual? So instead of treating all these people the same way, I will have different cohorts, and they have the same symptoms, but I'll treat them differently because of different reasons. Okay. So often people think about genetics, microarray data, or single nucleotide polymorphism. So genomics in general, metabolomics as well, or microbiome, what I have in the guts. But it's not only that. You can also use other kind of information. This is what I'm going to show you. So how does it work? You have a patient, for example, here, a new patient. And you want to know if this patient who has these characteristics in their file, will they reoccur? Will they have this disease again? Will it come back again and again? Some people it does, some people it doesn't. And you don't know if this person will have a yes or no for the recurrence of the disease. The only thing you know is this information. Well, you look at the history. You have other patients. And for those patients, you have these characteristics, same values for these characteristics, but you have the information whether that disease reoccurred or not. Well, from here, you can build a classifier with machine learning that will tell you yes, no, based on some information. And that classifier that you learned, okay, that cloud that I showed before, you will use it to classify this automatically, and it will say that's a yes or a no. Okay. So we can do it for many different things, and we here at UMA we developed many techniques for many applications. This is a case of all these are published. And this is the case of adjuvant treatment after chemotherapy for a woman who has breast cancer. So the biopsy, so to decide what kind of adjuvant treatment, you need to know if this person, so for example, for hormone therapy, you need to know if this person is ER positive or negative, because you will give this drug or that drug. Well, we can use also machine learning with the biopsy. You can do microarray data analysis on that biopsy, and you can get the gene expression for many other patients, and you know if they are ER positive or negative. For this new patient, now you have that information, and you can use the classifier to detect whether that person is negative or positive, and then you can decide whether you will give tamoxifen or not, or whether you give another treatment. And this can be done for many, many cases, whether it's breast cancer to predict whether somebody will have breast cancer or not, whether it will reoccur or not, whether this kidney transplant will work for this patient, will be rejected or not, prostate cancer, whether this patient with the radiotherapy will have this toxicity level or the other. You can predict lycaxia, so the loss of muscle mass. So all these were tried, and we have many interesting results. This is also using nuclear magnetic resonance spectroscopy. This is this is for metabolomics. This is with the urine test. You can also build a classifier and determine whether you can use it for diagnostic, but you can also use it for prognostic, for deciding what treatment and so forth. I'll talk about this another time when I'll talk about reinforcement learning. This is for diabetes. Here's another example where I'm not using omics at all. And this is the case we had with the Workers' Compensation Board. When people are injured at work, they go to the WCB for treatment at the clinic, and after the treatment, there is an assessment to see whether they're ready to go back to work or not. And more often than not, the assessment results into, well, we'll recommend another treatment before they go back to work. And what happens is there's a secondary treatment, there's an evaluation, and another treatment, and we could have a long iteration here before they go back to work. And that's expensive, it takes a lot of time, so they're not working, so the company is also losing money. And what we want to do is reduce it. How do you reduce it? By giving the secondary or first treatment the right one, so that we don't have to find another treatment. So we look at the data, injury, treatment 1, treatment 2, treatment N, and so forth. While some other cases, so there are cases where you have a long iteration, while other cases you have one treatment, an evaluation, they go back to work. It's very quick. So obviously here it means that the humans who recommended these treatments make mistakes. Okay? We don't want to have a very long one. So how can we learn from this, build a decision support system with machine learning that will, reading the evaluation, will tell you, oh, here's the treatment that I should recommend. Okay? So rather than the person scratching his head and say, okay, which treatment should I give? We get these evaluations. The evaluations are actually questionnaires that the nurse or the evaluator will fill in. And we use this, especially from those where it was short, when we know it's successful. And we learn a classifier that, given a new case, a new evaluation, will recommend treatment. Okay. Another interesting case that doesn't use omics at all. This is the case also that we did with the Cross Cancer Institute. Before going to surgery this is the case of brain cancer, and they need to remove the tumor. The doctor will look at slices of the brain, so these are scans, and with the tool will segment the area that will be either bombarded with X-ray or actually cut. Okay? They need to segment it in volume. It's a very tedious job. It takes about 30 to 40 minutes to do this segmentation in volume. It's not always consistent. The same doctor doing it in the afternoon or the morning is not the same. Two doctors is not exactly the same. It's a very tedious job. So what we did, we look at the past segmentations. And we learned how to do segmentation. And then we do the segmentation automatically. So that segmentation is not to replace the doctor who did the segmentation. That result is actually the starting point for the doctor to do the segmentation. Instead of segmenting completely, they just adjust it. And instead of spending 30 to 40 minutes, they spend 5 minutes. So it becomes a tool to help them do their job better. Now I'm going to skip all these. These are all their examples. So this is in case of changes. And basically I'm going to conclude. So I'll let you go. So AI is transforming completely, not just medicine, all the different activities for our future economies is completely changing. But AI is not the silver bullet. I mean, it's still in progress. We still have many challenges. Will definitely change medicine drastically. And in medicine, it doesn't just encompass genetics, but any other information that you can have in the medical health record. And I was hoping to have a little bit more time for questions, but hopefully if you have questions, you can ask me also next time we see each other, which is on Thursday. If you have questions now, you can ask
I
me.
just have a question.
Sure.
So whenever like supercomputers have like a lot of like GPUs, so like what's like the basic difference between GPU and CPU?
Well, the architecture is completely different.
Okay.
The architecture was designed for different purposes. And it happens that now the GPU, even though it was designed for these games to calculate very fast some ray tracing and things like that, it was useful to build neural networks, artificial neural networks. The CPU is not meant for that. It's more generic kind of processing unit.
Okay.
Yeah, and the GPU is more specific, more specialized.
Thank
And now they're building new, like Google in particular, they're building new processing units. They're not GPUs and they're not CPUs. They're called TPUs.
you.
But they're good not to learn, well, they're good to learn as well, but they're even better to do the inferences. Once you learned and you have a new object that you want to classify, the TPU is amazingly fast.
So it's a hidden network. It does the hidden network calculations.
It deals with these hidden layers in the network, yes. It's actually, the network is not really networks, it's all matrix multiplications. And the TPU is optimized for matrix calculations. So linear algebra. Well, thank you, and I'll see you on Thursday.
Yeah.
Hopefully the